Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar in Haryana. Today we will be talking about nonlinear Raman effect under the paper Atomic, Molecular and Laser Spectroscopy. After completing this, we will be able to understand stimulated Raman effect, hyper Raman effect, coherent anti-Stokes Raman scattering, surface enhanced Raman scattering, luminescence, Raman effect versus fluorescence, and spectra of polyatomic molecules. Stimulated Raman effect. A number of molecules from the initial state EI are excited to the final state EF when the incident light intensity becomes very large, and the Raman lines are also intense in comparison to that of ordinary light source. The molecules thus undergo two simultaneous interactions, one by the original light source with the frequency omega L, and then by the light originated from the Stokes lines with frequency omega S is equal to omega L minus omega nu, or the anti-Stokes lines omega ES is equal to omega L plus omega nu, where omega nu is the vibrational frequency of the molecule. Thus, if a Raman active material is subjected to an interaction with a high power laser like Q-switched ruby laser, the high power pulses induces gain in the medium at Stokes or anti-Stokes frequencies omega L plus minus n omega nu, where n can take the values 1, 2, 3, etc., shifted from the laser frequency omega L. A strong coherent light is built up at the shifted frequency, provided the gain is high enough to compensate for cavity loss. This parametric interaction leads to an energy exchange between the pump wave and the Stokes or anti-Stokes that further lead to parametric amplification. So, the power transferred to the first Stokes line omega S is equal to omega L minus omega nu related exponentially to the laser power at omega L. Hence, the first Stokes line rapidly become intense enough to act as a powerful source and give rise to another Stokes line. Omega L minus omega nu is equal to omega L minus twice of omega nu. This line is further intense enough to act as a powerful source and give rise to a third Stokes line, and so on and so forth. However, the generation of an anti-Stokes line does not arise as a downward transition from a populated upper state. The differences between normal Raman effect, which is also understood as linear Raman effect, and the stimulated Raman effect, the nonlinear one, are the following. In case of linear Raman effect, the intensities of Raman lines in the ordinary case are comparatively low as compared with the intensity of the pump beam, while in nonlinear Raman effect, these have almost the same intensity as that of the pump beam in this case. Raman gain may not be high in linear effect. While it occurs only at threshold pump intensity, it depends on the gain in the Raman medium and length of the pump region. In linear Raman effect, it does not require a pump frequency that is equal to the energy of the two levels, that is, the molecule is not excited to another real state. While in case of nonlinear Raman effect, the Stokes lines observed at frequencies omega L minus n omega nu, where n can take the values 1, 2, 3, etc., where omega nu is the vibrational frequency of the molecule, do not correspond to the overtones of the vibrational frequency. The observed Raman frequency are omega L minus 1 omega nu, omega L minus twice omega nu, omega L minus thrice omega nu, etc. Coming to hyper Raman effect, when a system is illuminated by an intense radiation from a giant pulse laser, say ruby laser or jag laser, omega L the frequency, scattered radiations are obtained at frequencies twice omega L, and twice omega L is equal to omega nu, and this is inelastic scattering.
In this case, the intensity of scattered radiations depends on the square of the laser intensity. These elastic and non-elastic scattering are known as Hyper-Raman-Rayleigh and Hyper-Raman scatterings.
Coherent anti-stock Raman scattering, CARS. It has now become possible to increase the efficiency of the Raman scattering by using near resonant incident radiation using the tunable lasers. The fundamental frequencies can be doubled, and some at difference frequencies are obtained using frequency mixing originating from the nonlinear terms in the polarizability. There is a mixing of three frequencies originating from the third order polarizability in CARS, wherein two lasers of frequencies omega 1 and omega 2 are chosen in such a way that their difference omega 1 minus omega 2 coincides with the Raman active vibrational frequency of the molecule omega nu. These incident waves are considered as the pump wave and the Stokes wave. The advantage is that the Stokes wave at omega 2 is already present as a part of stimulated Raman scattering to produce a large population density in the vibrational excited state. So this medium acts as a nonlinear medium for the generation of anti-Stokes radiation at omega as is equal to twice omega 1 minus omega 2 by the incident wave with a frequency omega 1. Similarly, Stokes lines with frequency omega s is equal to twice omega 2 minus omega 1 is generated by the incident waves omega 1 and omega 2. So it is to note that 4 waves are involved in this process of CARS. The molecules of anisotropic liquid, when placed in an electric field, tend to align themselves parallel to the direction of the field. As the molecules are not symmetrical, this causes the liquid to be anisotropic and birefringent. Birefringence results in splitting of light waves into two components with different velocities that causes different refractive indices for differently polarized light. This phenomena of electrically induced birefringence in anisotropic liquids is called the Kerr effect, where nitrobenzene is the most popular liquid being used for Kerr effects. The birefringence and hence a change in refractive index is proportional to the external electric field applied to it. This property is used in electro-optic shutters. When the birefringence is linear to electric field, the phenomena is called as Pockels effect.
Surface enhanced Raman scattering or spectroscopy, SERS. As the name suggests, this is a surface sensitive technique that enhances Raman scattering by molecules absorbed on rough metal surfaces. The enhancement factor is as high as 10 raised to the power 14 to 10 raised to the power 15. That allows the technique to be sensitive enough to detect single molecules. There are two primary theories, though their mechanism differ substantially. The electromagnetic theory proposes the excitation of localized surface plasmons, and on the other hand, the formation of charge transfer complexes by the chemical theory is proposed. The chemical theory applies only for species that forms a chemical bond with the surface, so it cannot explain the observed signal enhancement in all cases, whereas the electromagnetic theory can apply even in those cases where the specimen is absorbed only to the surface. It has been shown recently that SERS enhancement can occur even when an excited molecule is relatively far apart from the surface that hosts metallic nanoparticles, enabling surface plasmon phenomena. Now, another concept of luminescence. When the molecules of a gas are illuminated with light of a definite frequency, they go to an excited electronic state and revert to their initial state with the emission of discrete radiation of frequencies which is smaller than the frequency of the absorbed light. This phenomena is known as luminescence. In case the emission vanishes immediately after the removal of the exciting radiation, the phenomena is termed as fluorescence, otherwise it is termed as phosphorescence in case persists for an appreciable time. Their combined nomenclature is referred as luminescence. Fluorescence. In an absorption experiment at room temperature, the nu double prime is equal to 0 level of the ground electronic state is most populated and thus illuminating the molecules with continuous light. A single progression of bands in the electronic absorption spectrum due to transitions from nu double prime is equal to 0. So, nu prime varying from 0 to large value. For iodine molecule, which are heavy molecules, absorption transitions correspond to nu double prime is equal to 1, 2, etc. may be observed, though weak. The intensity distribution in these bands depends upon the shapes and relative positions of the two potential energy curves, that is governed by Frank-Kurdon principle. The figure is self-explanatory.
The absorption spectra display the pattern of vibration levels into the limit of dissociation, and the dissociation energy of the molecule in the excited electronic state can be deduced. There are now at least two different processes by which the excited molecule can lose its excess energy and return to its ground state. When the excess energy may be lost as heat by repeated collisions with neighboring molecules, no emission of radiation is observed in this process, that is referred to non-radiative process. In case the excited molecule return directly to the level nu double prime is equal to 0 of the ground state with emission of absorbed light, or to the other levels of the ground state with emission of light of lower frequencies, it is termed as fluorescence. Consider that a diatomic gas at low pressure, because at low pressure there are meager chances of molecular collisions, is illuminated with light having the frequency of a single absorption band. The absorbing molecules are excited to the vibrational level of the upper electronic state of this particular absorption band only.
The excited molecules then go over to the different vibration levels of the ground electronic state with emission of radiation. Thus, in the fluorescence spectrum, there is a single progression corresponding to nu prime is equal to constant of bands extending from the position of the absorption band towards lower frequencies with decreasing band separation. The molecules have not lost any energy in collisions before re-emission and thus termed as resonance fluorescence. The whole series of band is called the resonance series, and the band coinciding with the exciting absorption band is called the resonance band, and the such series of bands is observed in iodine-like molecules. There may be fluorescence band that has nu double prime smaller than that of the resonance or the exciting band. These bands lie on the higher frequency side of the resonance band and are referred as anti-Stokes members of the resonance series. Collisions become frequent if the gas is at high pressure, and in this case the molecules excited to a particular vibration level of the upper electronic state collide with the neighboring molecules of the fluorescent gas and lose or gain vibration energy, thus switching over to other vibration levels of the upper state. Transitions now take place from all these levels to the various levels of the ground electronic state, and the fluorescence spectrum consists of more nu double prime progressions corresponding to various nu prime values. It is noted that the absorption spectrum shows only one progression. Hence, fluorescence is more powerful technique than the absorption. Now, considering the fluorescence in solutions, the bulk of the molecules are in the lowest vibration level nu double prime is equal to 0 of the ground electronic state. The molecules are excited to various vibration levels of the excited electronic state on absorption of radiation. In the absorption spectrum, the lowest frequency band is the 00 band, and the spectrum extends to higher frequencies. The excited molecules lose vibration energy due to collisions, and most of them eventually come down to the lowest level, nu prime is equal to 0 of the excited electronic state before the fluorescence occurs. This is a non-radiative process and is called vibrational deactivation. Fluorescent emission then take place from nu double prime is equal to 0 level to the various levels of the ground electronic state and occur within 10 raised to the power minus 4 seconds after excitation. The fluorescence spectrum witnesses the 00 band is the band of highest frequency, and the spectrum extends to lower frequencies. The absorption spectrum displays the vibrational level of the excited electronic state, while the fluorescence spectrum displays those of the ground state.
Phosphorescence. Phosphorescence is a delayed emission and persists for periods up to seconds after the absorption process is ended. It is understood as a result from transitions that connect electronic states of different multiplicities. The figure depicts the mechanism of phosphorescent emission. Initially, the molecules of a sample are mostly in the lowest vibration level, nu double prime is equal to 0 of the ground electronic state in case of diatomic molecules, except oxygen. These are excited to another singlet electronic state upon absorption of radiation. Phosphorescence arises when a triplet excited state of the molecule exists between the singlet excited and the ground state, and its potential energy curve crosses the curve of the excited singlet state, as has been shown in the figure. The excited molecules can undergo radiationless transitions to a lower vibration level due to collisions at isoenergic states of the singlets and triplets. This is again a non-radiative process known as internal conversion, and the molecule is at triplet state. Further, vibrational deactivation by collisions in the triplet state takes the molecule stepwise down the vibrational levels until it reaches the lowest level of the triplet state. So, the transitions from this triplet state to the ground singlet states are responsible for the phosphorescence phenomena.
These transitions are, however, forbidden due to the spin selection rule delta S is equal to 0. Thus, these transitions have very long half-lives, and the resulting phosphorescent radiation is emitted seconds or even minutes after the initial absorption. There is a possibility of intermediate crossing electronic state. If it is also a singlet state, then the above process occurs very quickly and leads to fluorescent emission. Hence, both fluorescence and phosphorescence are the emissions due to the de-excitation of the molecules from the excited electronic states to the ground state. Fluorescence arises from transitions between electronic states of the same multiplicity, while the phosphorescence arises from transitions between states of different multiplicities, as the figure shows the singlet excited states and the triplet excited states. So, there is a crossing from singlet to triplet and then triplet to the singlet ground state level. Raman effect versus fluorescence. Raman effect and fluorescence resemble each other because in each case light suffers change of wavelength after falling on a scatter. However, Raman effect differs from fluorescence, as in fluorescence spectrum the frequencies are always less than the incident frequency. In Raman spectrum, lines with higher frequencies, that is anti-Stokes lines, and lower frequencies, that is Stokes lines, are observed. In case of fluorescence, frequencies of scattered radiation is independent of frequencies of exciting radiation. In Raman spectroscopy, the scattered radiation is directly related to the incident radiation frequency. Fluorescent lines are unpolarized, while Raman lines are strongly polarized. Fluorescence is due to real electronic transitions, while Raman scattering is due to virtual electronic transitions. Raman spectrum is more informative than fluorescence spectrum. Fluorescence is an absorption and re-emission process. Raman scattering is an inelastic scattering process.
Spectra of polyatomic molecules. The values of force constants are to be calculated from the observed vibrational frequencies. Though there is only one vibrational frequency for diatomic molecules, but the vibrations depend upon the number of atoms in a polyatomic molecule. If a molecule contains n atoms, there is a need to specify by 3n coordinates, that is 3 coordinates for each atom. The potential energy being a function of the relative position of the atoms, one can conveniently transform into internal coordinates and separate out the motion of center of mass. The center of mass has 3 degrees of freedom under translational motion and thus leaves 3n minus 3 internal degrees of freedom for the molecule. There are either 3 or 2 rotational degrees of freedom depending on whether the molecule is linear or non-linear. So for a linear molecule, 3n minus 5 vibrations exist, while for non-linear molecule, 3n minus 6 vibrations exist, n being number of atoms in the molecule. So considering a polyatomic molecule, suppose water, H2O, the number of vibrational frequencies expected are 3 into 3 minus 6. It comes out to be 3. Experimentally, due to the complexity of the spectrometer, otherwise due to symmetry considerations, these frequencies may not be observable sometimes. But by combined effect or the effort with infrared and Raman spectra, the fundamental frequencies can be identified. A theoretical calculation of the frequencies and the amplitude of motion can be made by formulating the kinetic energy and potential energy of the molecule in matrix form. These calculated values of the amplitudes of vibrations can be compared with the experimental values obtained by other methods like electron diffraction.
The fundamental frequencies of vibration obtained from infrared and Raman spectra provide considerable information about the interatomic forces in various molecules. It is to note that different types of valence bands exhibit different degrees of resistance to stretching and bending that are roughly independent of the molecule in which the bond occurs. Further, there are empirical relations between the length of bond and its resistance to stretching that gives useful results. The figure shows the stretching, symmetric stretch, symmetric bend and antisymmetric stretch in case of water molecule H2O. There is another type of spectroscopy which is termed as nuclear magnetic resonance spectroscopy, shortly NMR, also yields a lot of information in this direction, where microwave and infrared are extensively used for such studies. The preferred relative orientation of portions of molecules connected with single bonds has proved to be of decisive consequence in the activity of important biological molecules and has posed a challenge to theoretical chemists to attempt an explanation of the system. Although infrared, Raman and magnetic resonance studies are quite useful, but the experimental tools like microwave and gas phase electron diffraction techniques are most helpful. The study of the molecular energy levels can provide a number of physical and chemical properties of molecules, and the information thus obtained is very important for a chemist, a biologist and an astrophysicist or a space physicist, and even in forensic laboratories. Now coming to vibration, it has been seen that the number of internal vibrations of a molecule with n atoms is 3n minus 5 for linear molecules and 3n minus 6 for non-linear molecules. In the case of linear or non-linear molecules with n atoms, there are n minus 1 bonds between its atoms, and hence n minus 1 of above vibrations are bond stretching, and the remaining 2n minus 5, that is non-linear, and 2n minus 4 for linear are bending motions. In case of diatomic molecules, there is a particular case of linear molecule. The number of constituting atoms are 2, and hence the number of vibrations 3n minus 5 is equal to 1, and hence there can be only one fundamental vibration. The presence of voltones is due to anharmonicity of the molecule. These vibrations are normal modes of vibrations. A normal coordinate is a single coordinate along which the normal mode of a vibration can be followed. The vibration doesn't cause a translation of center of mass of the molecule. It is a linear combination of the motions of the individual atoms. If we have a simple diatomic molecule, say HBr, the H nucleus will move 79 by 1 times fast as that of 79 Br. So Q is equal to R minus R naught is equal to delta R H plus delta R bromine, and MH delta RH is equal to MBr delta R Br, and so on. Taking the ratio delta Br upon delta RH is equal to MH by MBr, that is mass of hydrogen upon mass of bromine. Mathematically, the normal coordinates are expressed such that the potential energy V is equal to 1 by 2 sigma lambda I Qi square, where lambda is a constant and kinetic energy K is equal to half sigma Mi dQi upon dt square. If we consider a nonlinear triatomic molecule of the type AX2, there are 3n minus 6 is equal to 3 vibrations.
All 3 atoms vibrate with the same frequency in a normal mode. The example for an AX2 type is the water molecule with the chemical formula H2O. Among the 3 possible vibrations, 2 are symmetric and 1 is antisymmetric. From the figure of symmetric vibrations, it can be seen that if the molecule is rotated in an axis which bisects the HOH angle, the appearance of the vibrations look alike before and after this kind of rotation. Such kind of vibrations are called symmetric vibrations, and the axis of rotation is called a C2 axis, as by rotating about 360 by 2 is equal to 180 degree of the molecule still have the same appearance, and by rotating twice the molecule attains the original position. It is clear from the figure that the nu1 symmetric stretch and nu2 symmetric bending are symmetric vibrations, and nu3 is an antisymmetric stretch. Further, all these vibrations are infrared active. For an infrared active, there must be a dipole change during the vibration. The dipole change may be parallel or perpendicular to the symmetry axis. In the case of symmetric vibration in water molecule, the dipole changes along the direction of the symmetric axis C2, whereas in the case of antisymmetric stretching, the dipole change is perpendicular to the axis. So, carbon dioxide molecule is a linear triatomic molecule, and hence the number of vibrations in it are 3n minus 5, which is equal to 4. So, there are 2 sets of symmetry axes in this molecule. The carbon atom occupies the middle position and has a 2-fold axis, C2 perpendicular to the bond axis, and an infinite fold axis, C infinity, passing through the bond axis itself. It is called C infinity, as by rotation of the molecule about this axis in any single axis in any angle gives identical appearance of the molecule.
The different kinds of vibrations in the CO2 molecules have been shown in the figure. In the case of nu-L symmetric stretch, there is no dipole change due to vibration, and hence it is not infrared active. Among the 4 vibrational modes expected, the nu2 bending mode consists of 2 vibrations, one in the plane of the paper and the other perpendicular. The oxygen atoms of CO2 molecule move perpendicular to the plane, that is into and out of the plane. These are called degenerate vibrations, as these are 2 independent vibrations and the frequency of these vibrations are the same. When the molecules are considered as anharmonic oscillators rather than harmonic, several overtones of the type 2 nu1, 3 nu1, 4 nu1 or 2 nu2, 3 nu2, 2 nu3, 3 nu3, etc. or combination bands like nu1 plus nu2, twice of nu1 plus nu2, etc., or difference of the bands of the type nu1 minus nu2, nu1 plus nu2 minus nu3, and so on, etc., are also observed. Coming to rotational spectroscopy of polyatomic molecules, the rotational selection rule for a polyatomic molecule depend on the nature of vibration, that is, either it is parallel or perpendicular, or in other words, the dipole change along or parallel to the symmetric axis or perpendicular to the symmetry axis. The selection rules for a parallel vibration in the case of linear molecule, assuming that the molecule undergoes an harmonic oscillation, are delta nu is equal to plus minus 1, plus minus 2, plus minus 3, and delta j is equal to 1. Thus, R and P branches are obtained as in case of certain diatomic molecules. The lines are equally spaced, ignoring centrifugal distortion and without having line occurring at the band center. As B value is comparatively smaller in the case of polyatomic molecules, the spacing of the lines in the two branches is quite small. In heavier molecules, the rotational constants are smaller and therefore R and P contours are observed. An estimate of the rotational constant can be divided from the separation of the two contours. For a perpendicular vibration of a linear molecule, the selection rules are delta nu is equal to plus minus 1, plus minus 2, plus minus 3, and delta j is equal to 0, plus minus 1. Therefore, there are three branches of lines R, P, and a Q branch. Q branches are superimposed at the origin and therefore are intense. The molecules with zero dipole moment do not show any pure rotational spectrum but show infrared spectrum. If the spectra exhibits rotationally resolved structure, one could obtain the rotational constants. In the case of linear polyatomic molecules like CO2 or C2H2 with a center of symmetry, the rotational spectrum observed in the Raman spectrum is very much influenced by the nuclear pins. In the case of CO2, alternate rotational lines are missing as the nuclear spin of the oxygen is 0, and the case of acetylene, intensity ratio of nearby lines are 3:1. Thus, the P and R branches lines show strong, weak lines. In the case of a symmetric top molecule, the energy for a rotation vibration line may be represented by, thereby neglecting the centrifugal distortion, E nu j is equal to E vibrational plus E rotational is equal to omega E xc nu plus 1 by 2 minus omega E nu plus 1 by 2 square, and so on, B j plus 1 minus A minus B k. Here again the change of dipole moment parallel to symmetry axis gives rise to parallel bands, and the dipole change perpendicular to symmetry axis give rise to perpendicular bands. And the selection rules for parallel vibrations are delta nu is equal to plus minus 1, plus minus 2, plus minus 3, etc., and delta j is equal to 0, plus minus 1, and delta k is equal to 0. And for perpendicular bands, delta nu is equal to plus minus 1, plus minus 2, plus minus 3, and delta j is equal to 0, plus minus 1, while delta k is equal to plus minus 1. Thus, in both cases, we have R, P, and Q branches of.
So, let us summarize what we have learnt in this module is stimulated Raman effect, hyper Raman effect, coherent anti-Stokes Raman scattering, CARS, and surface enhanced Raman scattering, SERS, luminescence, under which we have learnt about fluorescence and phosphorescence, Raman effect versus fluorescence, and spectra of polyatomic molecules. Thank you.